Hello, this is Brian Washburn. I'd like to talk about damped oscillations. Okay, so let's consider a system where I have a mass in a spring system, and I'm going to define x as the horizontal or the displacement of the spring. Okay, and what I'm going to add, and then I have a restoring force of the spring, which is Hooke's law. Okay, so everything looks like simple harmonic motion, except now what I'm going to do is I'm going to add a dampening force to this. Okay, so you might think, okay, what is the functional form? And I'm going to choose a dampening force of the term that's proportional to the velocity of it. Okay, so I have a linear resistive force acting on this block. Okay, so that's the problem I'm going to solve. Now, you may ask, okay, well, is it really appropriate to use this type of force? Remember when we talked about resistive forces, objects like oil drops or water drops, they experience linear air resistance more strongly than quadratic air resistance. So isn't it more appropriate if I have an object like a box, should I have this as V or V squared? And that's a good question. Really, we should probably be using a quadratic air resistance, but that makes the problem very difficult. So again, what I want to do is just look at oscillations that are damped, and to make things much more simpler, I'm going to use a linear, excuse me, a resistive force that's directly proportional to velocity. Okay. The other thing about this particular system is this is no longer it's a non-conservative system, meaning that energy is lost. And this force here is going to do work on the system. And since this, and you think about this force here, okay, well, is this a conservative force? Obviously not, because it depends on velocity. Thus, energy is not conserved. So this force is going to do work on the system and take energy away from the system. And then eventually we're going to lose all mechanical energy. All the mechanical energy is going to go somewhere, okay? So let's write down our equations of motion, and we're going to talk about solutions to that equation of motion. What it can do is it can say, okay, mass times acceleration is going to be equal to, well, the restoring force is minus kx, and then the resistive force is going to be minus bx dot, where b is some coefficient that determines the strength of the resistive force. And you may say, well, why do we have the minus sign there? Well, if say for example the velocity is negative at a given time, that makes this a negative number. That means it points to the left, where the resistive force must point in the opposite direction to the right. So again, negative times negative, that gives me a positive. And so that gives me the correct direction. Okay, so now what I can do is I want to write down a second order differential equation. And what I'm going to do is write it like this, and then I'm going to define a couple things. First, I'm going to define the natural frequency squared, that's just k over m. And then I'm also going to define a constant beta b divided by m as 2 beta. Okay, and so then I get a differential equation of the form x double dot plus 2 beta x dot plus omega naught square equals x. Okay, so we can identify that as a second order ordinary differential equation, or more specifically, a homogeneous second order ODE. So we've already talked about how we're going to solve this differential equation. What we're going to do is we're going to choose an exponential solution, put it in, get a characteristic or auxiliary equation, and solve for the roots. So if I put that auxiliary, and we're not going to do it since we did it before, but what I do is if by substituting that solution, I get an auxiliary equation of this form, and then I look for the roots. So in general, what I have is a very general solution given by the expression I have here. All right. Now, that doesn't tell us very much. There's not much physics there. That's just a solution to a differential equation. So what I'd like to do now is look at physics going on. Okay, now let's just talk about the terms beta and omega. Okay, and by the way, yeah, so if you take a look at the units of the beta and omega, okay, hold on a second. So if we look at this equation, notice that all these things, when I add them up, have to have the proper units. So this is x double dot. It has units of meters per square. Okay, meter per second square, I should say. Now, if you take a look at this term here, let's write it off to the side so we understand what the units are. So we have units of whatever beta is, and we're going to figure that out. And then x is units of meters per second. So that must mean that beta has to have units of 1 over second in order for the product of the two to be equal to meters per second squared. Then I have the last term I have here is omega naught squared times x. Well, x has units of meters. So that must mean omega naught has units of 1 over second squared. And so omega naught has units of 1 over second. So the important thing is that beta and omega have the same units. Okay. And that's going to be in, well, that's pretty obvious because if you look at down here. Okay, first of all, we can see here that since we're adding this squared plus this, that must mean they have the same unit. Also, we can see from the exponential here that beta, the product of beta times t, has to have unitless, so beta has units of 1 over time. So that's nice. So now what we're going to do is we're going to look at solutions to this where we're comparing beta to omega. Okay, and again, let's physically think about what is beta. If you take a look at this term here, beta had this negative exponential, and also beta is related to b. Okay, beta is a rate of, remember, this force does work on the system to remove mechanical energy from it. So b, and thus beta, is a rate of how much that force takes away energy from the system. Okay, so this is some kind of dampening. In fact, we can define a time. For example, tau as 1 over beta, and tau is going to represent how fast energy leaves the system. Okay, omega. Well, we already know what omega is. Omega is a frequency, or a natural frequency, that determines how fast the system is going to respond. So there's two time scales we can look at. First of all, we can define, say, a tau. A tau we can define as 1 over beta. And that tells me how much energy is lost. So this is a rate of energy lost. Okay. Okay. Now what about, we can define a natural period. A natural period is going to be, we've done this before, 2 pi divided by omega naught. Okay. And you think about, what does this tell me about the energy? Well, this tells me about the energy is that it kind of tells me how fast energy gets converted from potential to kinetic and vice versa. Okay, so that tells me something about how the rate of energy is transferred between potential and kinetic energy. Okay, so it gives me information about the mechanical energy. Okay. So that's kind of cool. So those two time scales have some physical meaning. All right. So now what we're going to do, we're going to look at solutions. So what we're going to do is we're going to look at solutions for 3 different cases of comparing beta to omega. Now remember, if we said beta equal to 0, that gives us simple harmonic motion. So I'm going to look for a case where beta is less than, smaller than the natural frequency. Okay. And we're going to call this the underdamped case, and we'll show you why. Second, we're going to look at a case where beta is equal to omega. And third, we're going to look at a case where beta is bigger than omega. Okay, so those are my 3 cases. Let's take a look at the underdamped solution. Okay, so now, going back, remember, what I'm going to do is, this is my generic solution here. Completely generic. Now I'm going to look specifically at the argument of these for the case, for those 3 cases. The first case is, now we're going to look at where beta is less than omega naught. Now, since this is a smaller number than this, I'm going to get, this is actually a completely imaginary number. I'm going to factor out a -1 from here, and then bring that out. That's going to give me I. And so then this term here is a real number. I'm going to call the square root of this term omega 1. If I stick that back into my differential equation solution I showed before, I can rewrite it as, well, I have this constant in front, and then I have C1 exp of plus I omega 1 plus minus that. Now notice that these guys here from the Euler relationship, those are sines or cosines. And C1, C2 are dependent on my initial conditions. So given, I can always rewrite this as cosine omega 1 t minus some arbitrary phase. And again, in this case, A and delta are going to be determined by the initial conditions. Okay. Now, what is omega 1? Omega 1 is the frequency of the oscillation, which is defined by this. Okay, so if I were to plot this, take a look. It's just a constant times an exponential k times cosine. Now I'm going to get some shape. So say what I do is I say x is equal to x naught at some time t equals 0, and the speed is equal to 0. at times t equals 0. So I'm going to get a shape that kind of does this. An exponential, and it's going to be exponential k around it. Now the rate that I'm going to lose amplitude is going to be given by e to the minus beta t. And then things are going to oscillate. Now they don't oscillate at the natural frequency. They're going to oscillate at omega 1. Okay. So we can look at this. Let's actually plot this out for a specific condition. And what I'm going to do is I'm going to do this. And so I have code here called physics 522 damped oscillator. And what I'm going to do is I'm going to set my natural period. I set up my condition so my natural period is actually 1 second. Okay. And you can see here I typed in T0 is my natural period, the period, and that's 1 second. So I just arrange K, remember K over M such that I get a natural frequency of 1. Okay. Now what I'm going to do is I'm going to choose, sorry, I can't write beta in code, but the B is actually beta. And I'm going to set beta equal to a number that's the natural frequency divided by 4. Okay. And if I plot this out, notice what I get is I get this kind of shape right here. Okay. And that's kind of what I expect. Now what we can do is we can define a couple times. Remember the omega 1 is the rate that this goes by. And what I do is I set omega 1 is given by this expression here. That's what we wrote down. And then I'm going to define a time associated with that. Well, that's just going to be 2 pi divided by the frequency. And if you take a look at T1 is that time associated with omega 1. It's 1.032. If you look at the natural frequency, it's 1. So T1 and T0 are very close to each other for this particular case. And that's going to be pretty much true, okay, for the problems we're going to see. Now what is tau? Tau is 1 over beta. And notice that it's smaller. Okay, so basically what it means is that this thing is going to oscillate faster than the decay is going to be. Okay. And in fact, what we can do is we can just kind of sketch out the decays on either side of it and replot it. And you can see here, this line here represents the decay of e to the minus beta. Same thing for here. And then the oscillations are kind of fixed between those regions right there. So that's an underdamped case. Underdamped case. Now the motion repeats a little bit and eventually dies away. And that's because the resistive force is taking energy away from the system. Okay. Now let's look at the critical damped case. The critical damped case is where beta is equal to omega naught. Now the thing is, now I get 1 root. And so that's if you go back to my generic solution, which is way up here, it looks like I only have 1 solution. Well, we can't do that because then I really need 2 linear independent solutions for this differential equation. So I have to guess another, or I have to use another linearly independent solution. So what I do is I say x naught is equal to C1. Since there's 2 constants, I need 2 linear, since second order differential equation, I need 2 linearly independent solutions. All right. So then I can choose that. So the first one is just going to be c to the e to the beta times t, and then my second one is going to be c2 t times that quantity there. And again, I'm going to use the initial conditions to get c1, c2. All right. Now, if I get a case where, say, initial speed is equal to 0, but I have some initial position at times t, I'm going to get something that looks like an exponential k, like that. If I have another case where, say, it starts at x equals 0, but it has an initial speed, it's going to come up and then eventually come down exponentially. Okay. So this is called, why is it called critical dampening? Because this is the case where I have the fastest rate of energy lost. I'm going to have the fastest rate to 0. Okay, that's why it's called critical. And in fact, the behavior is not even oscillatory. Never cut in this well. I think for most cases, it's just going to come. It's never going to cross the 0. It's not going to oscillate. Okay. So we can look at that. So what I'm going to do is let's go back to my code, and what I can do is I can easily look at that, and the way I'm going to look at that is just set this equal to each other like that. Okay. If I run it, And then as you can see here, it goes blah, like that. All right. So that's a case where I have initial position but no initial speed. All right. Why not? Let's just try, let's make this, let's try to look at the other case. And then let's see what it gives me through this. All right, so I'm going to get initial speed but no initial position. Yeah, and you can see I get the shape that I showed you before. Kind of comes up and comes down. And again, that factor tau determines how fast energy is lost, and it goes down. Okay? So let's go back to what I had before. Sorry about that. Oh, what is that? Okay, too many buttons here. All right. Now let's look at the final case. I'm going to choose beta bigger than omega naught. That means I have a very strong dampening. Nothing special here. The solution, I can't write any different than what I have the general solution. Okay, so again, I write this in terms of the exponential decays. And so what I see is that I'm going to see something that's going to come up and is come down eventually. Now what's going to happen here is overdamped means that I have so much dampening that, well, in the end, I'm not going to be, my rate of going to zero is not going to be as fast as the critical dampening case. All right. So what we can do is we can do that here as well. What I can do, going back to my code, I'm going to set beta equal to 4 times that. All right. And let's solve and see what happens. And you can see here, it kind of comes down eventually. Okay. But not as strongly as the critical damp case. Okay, so it sits here, and then even over 2 seconds, it's not totally there. In fact, what we can do is let's write down what is tau. Tau is that. So tau is a pretty damn small number. Compare that to 2.0. Okay, so it's much smaller than this. Okay. Okay. So that's it. So again, what we did was we looked at a particular oscillatory system that has a resistive force that's directly proportional to the speed of the object. We get a second order differential equation, it depends on this, and we get a generic solution using a method that we used before. And then in order to describe the physics of this particular solution, we have to compare beta to omega naught, where beta represents the rate that energy is lost. Omega naught represents a rate of how energy is transferred between potential and kinetic energy. Okay, so we'll talk to you next time. Bye-bye.